So let's imagine this. Let's imagine that I have two ions. So I named them A and B. Okay, don't forget what an ion is, right? It's either charged positive or it's charged negative based on the number of electrons it has, right? So when we have two ions like this, one is positive and one is negative, what do you think happens, right? What is it that can happen between two ions that come closer together and both of them have a opposite charge? One is positive, the other one is negative, right? What's going to happen is that they're going to attract each other, right? So it'll be an attraction between the two of them. And there is a name for that. When two ions get together and form that something that we call a compound. And what is a compound? A compound is made of several atoms, right? So atoms interacting with one another. Some of these compounds are super simple, such as sodium chloride, table salt, right? So we would have, for example, in table salt, the positive side of the table salt, not the table, but the table salt will be sodium. So that's the symbol for sodium. And then on the other side, we have chlorine. That's called sodium chloride, right? So table salt is sodium chloride, and it is when you salt something, you had your salt on anything, those crystals are made of two atoms, two ions connected with one another. One is positive, the other one is negative, and that compound that we call salt is possible because of an ionic bond, right? So that what we see here, this interaction between the two ions, is called an ionic bond. Okay, so charges attracting one another, forming a compound, two ions, that's called an ionic bond. So we have seen that two ions can interact with one another, right? So if we have on one side we have positive, and then on the other side we have a negative charge, we know that these two parts can attract each other, and that's called an ionic bond, or ionic bonding. So ionic bonding exists. We see this over and over again in nature. That's found everywhere. Another type of bond, and a very, very important bond, it's very solid. Ionic bonding is not very, it's not very solid. It's not very strong, I should say. There's another kind of bond that's really, really, really strong, and that bond is called covalent bond. And I'm going to explain that to you and see what that means. Okay? So let's imagine that we have two atoms, different atoms, and let's call that atom A here, and then we have atom B right here. So let me draw this B again. So atom B, atom A and atom B. And we know that the atoms, I'm having problems with my pens. There we go, that's better. So let's say that atom A has electrons on the outside. So remember, there's a nucleus, and then these electrons somewhere at the orbitals are orbiting around the nucleus, right? And we have the same thing for atom B, right? So let's say that those two atoms are not necessarily ions, right? So what could happen is that it would be possible for some of those atoms to share electrons with one another. That's interesting, right? Don't forget that electrons are at the periphery of the nucleus. Those are on the outside of the nucleus, somewhere around, in some space. And it is possible for those atoms to be shared between those two. Okay? So how is that possible? Well, it is possible because of this. So let me explain something to you, is that when we look at any atom at all, any atom, so let's say atom X right here, right? So the electrons around an atom are organized in a certain way. They occupy something that we call an orbital, right? We've been through this already. What you need to know is that there's different levels of orbitals. We would say that there are electron shells. The first level can contain 2 electrons, okay? 2 electrons. So that is the first level, and I'm just going to say that it's like circle around the nucleus right here. The second level can get up to 8 electrons at the most, okay? So we would have, say, we could have like one here, here, 2 more, and then those here. So this second shell right here would be full when there is 8 electrons. Now, is it always full? Of course it's not. Sometimes it's missing a few electrons, right? So what I want you to understand here is that the atoms want to, so of course they have no will, they don't think, but naturally they will have a tendency to fill this second shell. So if the first shell is already occupied by 2 electrons, the second shell can have up to 8. But say that there's only 6 because 2 are missing, it will want to interact with another atom that has 2 electrons it can share in order to fill this orbital here. So what it might want to do is interact with another atom in order to grab the electrons, or not necessarily grab them and steal the electrons, but actually share these electrons with the compound. Okay? So let me draw something else here. Okay, so that's a very important concept. So what we would have is this. We would have, say, an atom A, and then we have an atom B, A and B, right? And then we would have one electron missing, for example. So this electron would be shared between those 2. So don't forget that the orbitals are here, and the orbitals are around the nucleus of each atom. And this is where we find the electrons, right? Well, it would be possible for these electrons to be shared in an area between those 2 here. So basically, what the 2 atoms are doing is that they're cooperating together in order to make their outer shell complete, or as complete as possible. So when 2 atoms like this are sharing the electrons, we say that is a covalent. Covalent, co as in collaboration, together, covalent bond. And this covalent bond is very, very strong. It's the strongest bond between 2 atoms that we can get. And this is very important because most, I would say, like molecules and compounds, or many compounds, are made of different types of atoms interacting with one another, and they are interacting through covalent bonding, as we can see just here. Okay, so that is a very very important concept. Another very important concept to understand here is the concept of polarity. And polarity as opposed to neutral, and also as opposed to non-polar. Okay, non-polar. Not so much neutral, but non-polar. So polar versus non-polar. So whenever we have a charge, so whenever we have a positive or a negative charge, this is polar. But when there's no charge at all, this is nonpolar. That's a very simplified, I probably would say oversimplified definition of what polar versus nonpolar is. But let me get to the point and the reason why I'm explaining this to you today. So, let's look at a very, very special molecule, and that molecule is known as H2O, right? So H2O, and then many of you have now recognized that H2O is the chemical formula for water, right? So we know that H2O is water. What it means is that we have an atom of oxygen right here, so that's our oxygen right here. And then we also have connected to this atom, we have two hydrogen. Now what's the type of bond right here and right here? This is covalent bonding, right? So what happens here is that the electron between, there's electrons that's being shared between the oxygen and the hydrogen right here. So we have a space right here where we have the electron, and then we have the same on that side here. Okay, so that's very important to understand. Now, another thing, and this will bring me to the polarity definition, is that when you think of covalent bonding, there's different ways of looking at it. There's different versions of covalent bonds. Now let's go back to water, right? So I have my oxygen right here, and then I have my hydrogen here, and hydrogen right here. So H2O, as I have mentioned, and then we have our bonding right there, okay? Let me just draw something on top of that. So let me just get my red pen here to explain something to you, is that the electron in a covalent bond will spend its time, right? The electrons, or electrons, depending on how many electrons there are, but we'll spend the time between this part and this part here, right? So it's in between somewhere in there. We don't know exactly where it is, right? But we know it's spending some more time in there. What's interesting here is that the oxygen is a kind of a special element. It really likes electrons, right? So it will pull. So it wants to complete its outer shell that could have up to 8 electrons. Remember that, right? So it wants to complete it, and more than the hydrogen wants to. And the hydrogen doesn't even have a second shell. It only has that tiny shell around it where 2 electrons can occupy that's first shell. Remember, there's 1 shell and the second one that has 8 around it, right? So the oxygen has more affinity for the electron than the hydrogen has, right? So if I draw an area in which we would find the electron, like this, at any given time, you see that the electron will spend more time closer to the oxygen than it will to the hydrogen, right? So the electron is attracted more to the oxygen than it is to the hydrogen. So remember what happens when an atom loses an electron? It becomes charged positively, right? Losing a negative particle causes it to become positive because of the proton numbers, right? Remember that, right? That's important. So what happens here is that the hydrogen is not really losing the electron because it's still attached to it. It's just shared between the oxygen, right? It's shared right here. But the electron spends more time here. So if we could look at it, we would say that this region is a little bit more positive than this region here on the oxygen, and that region right here is a little bit more negative. It's not really negative. It's just more negative because the electron spends more time here. So here, what we have here is an element of what we call polarity. So this is known as a polar covalent bond. Okay? Polar covalent bond. As opposition to neutral or nonpolar covalent bond. So for example, I can have the formula for methane, right? So the molecule methane. Methane is a carbon compound, so it's carbon right here. We have an atom of carbon in the middle. And then we have 4 hydrogens at the periphery of this atom here. And then the electrons are shared between the carbon and the hydrogen, but it's shared equally. The carbon is not pulling more on the hydrogen than the hydrogen is. So it's equal. So there's no polarity to this. But you see that water has polarity. Now, I really want you to remember that, because over the next few slides, we will talk about polarity of water and the reason why you and I are alive today, right now, at this moment. And the reason why you see all the plants and all the animals and life is possible is because of polarity of water. Okay, so that is a very, very important concept to remember. Remember, polarity of water, right? A polar covalent bond versus a neutral or nonpolar covalent bond. Now let's look at the concept of something that we call hydrogen bonds. So remember, we looked at ionic bonds, we looked at covalent bonds. Now I want to introduce another concept which is known as hydrogen bonds. Okay, so hydrogen bond is, I know I say this all the time, but that is a very important and very, very cool feature of molecules, including water. So what I have here is my molecule of water. So we have H2O right here, right? H2O as oxygen, right? So in red, oxygen, and in blue, we have hydrogen right here connected to it. So it gives this kind of like shape of molecule. And we know that positive and negatives will attract each other, right? So say that you have a beaker or a glass of water with just water in it. So there's billions and billions and billions of water molecules like this floating around. Well, I want you to know that water doesn't look like there's any structure to it, but there is, okay? Every single water molecule is interacting with the next one, and then the next one, and the next one. So let me explain what I mean by that. So since this is a polar covalent bond, we know that part of the molecule has a tendency to be more negative than the other part. So if this one is more negative than the other part of the molecule, where the hydrogens are, will be more negative, as we can see here, right? So hopefully that still makes sense to you. Now, since there are many molecules of water inside your glass of water or your beaker, they will interact with one another. They're not independent anymore and just floating around and just moving around, because molecules are always moving. So because of the charge, they will organize themselves and interact with one another. So here's what's going to happen, right? Since we have a negative charge here, what's going to happen to the next water molecule that we will have here, right? So here's what's going to happen. So I will have another water molecule here, and that other molecule of water will have its hydrogens right here, but since they have more of a positive charge, remember it's not a real positive charge, but we will have some kind of an interaction between that, right? Between this part here, which is molecule here, and this molecule here, there will be an attraction between the two of them. And then it will be possible for another molecule here, molecule of water again, this one and this one, it will be possible to have another bond right here, right? It's not a real bond, it's an interaction. They're positive and negative. They are attracted to one another. Doesn't mean they're going to stick together, but they will organize themselves in some way. On the other part is the same here. These hydrogens right here will now be interacting with the oxygen of this water molecule right here, right? So we will have an interaction right here. So you see that it is possible for many molecules, including water, to interact with one another. It doesn't mean they are tethered to one another, they're not attached to one another. It doesn't mean they're contacting each other. It just means that they are in space and they occupy that space and they have some kind of organized structure to it because of that. So if I threw in a molecule of water here, randomly floating around, it would eventually be attracted by one of those molecules here and orient itself in such a way where we would have something that would look like this and an interaction there. So that is known to be hydrogen bonding.